When a body moves in a circle of radius r with a constant speed v, it doesn't actually move in a straight line. It keeps changing its direction, and that means there is acceleration directed towards the center of the circle. We call this centripetal acceleration. Mathematically, it is written as acceleration equals v squared divided by r. According to Newton's second law, the force needed is F equals mv squared divided by r. This force is always directed towards the center, whether it is a stone tied to a string or the earth revolving around the sun. Now, you might wonder, where does this force come from? Well, that depends on the situation. If Fx is equal to Fx, you are swinging a stone in a string, tension in the string provides the centripetal force. For planets, it is gravity that pulls them towards the sun. And when a car takes a turn on a road, it is friction between the tires and the road that plays the role. Without this force, no object can move in a circle. Instead, it would fly straight off. Let's make this more practical. Imagine a car moving on a flat horizontal road. Three forces act on the car: weight mg acting downwards, normal reaction enacting upwards, and frictional force acting sideways towards the center of the turn. Vertically, the forces balance each other, so N equals mg. That means the centripetal force entirely comes from the frictional force. The condition for a safe turn is that mv squared by r must be less than or equal to mu n. This inequality sets a limit for how fast the car can go without slipping. From that condition, if Fx is equal to Fx, we cancel out mass, we get v squared less than or equal to mu gr. This gives the maximum safe speed as v max equals square root of mu gr. Notice something important here. This maximum speed does not depend on the mass of the vehicle. Whether it's a small car or a heavy truck, as long as the coefficient of friction and radius of the turn are the same, the speed limit is identical. But there's a smarter way to design roads: by banking them. On a banked road, the surface is tilted at an angle theta. This way, part of the normal reaction itself provides centripetal force. When friction is negligible, the ideal condition becomes tan theta equals v squared divided by rg. Banking makes turns safer, especially at high speeds, because now vehicles don't have to rely completely on friction. Let's solve a real problem together. A car moves at 72 km per hour on a curved road of radius 50 meters. What is the required banking angle? Step 1. Convert speed. 72 km per hour equals 20 meters per second. Step 2. Apply the formula. Tan theta equals v squared divided by rg. Step 3. Substitute values. Tan theta equals 20 squared divided by 50 times 10, which is 400 divided by 500, equal to 0.8. Step 4. Find the angle. Theta equals tan inverse of 0.8, which is approximately 38.7 degrees. Rounding off, the required banking angle is about 39 degrees. So let's quickly revise. Centripetal force is always required for circular motion, and it always points to the center. On flat roads, friction provides this force, and that sets a limit for maximum speed. V max equals square root of mu gr. On banked roads, the normal reaction helps, making high-speed turns safer. This is why road engineers carefully design curves with banking so that vehicles can turn smoothly without skidding.